Start with David Timos, who is a local. So he's going to present the economies of energy efficiency and conservation in a variable renewable energy system. Please.
Thank you. So the question here, the main topic is how valuable is it to have conservation or energy efficiency in this particular context, the context of an energy system that is almost or fully supplied by renewable energy sources, some of which are variable. So the context is a little bit complicated, and it's important, and most of the presentation is actually about the context, but we will circle around to efficiency and conservation toward the end of the presentation. So the assumption here is that the world needs decarbonized energy systems, and this is a cost-effectiveness analysis, which means the question is how to get those carbon-free energy sources at the lowest possible cost. Not directly looking at the benefits, just assuming that we need to do this. What's the cheapest way to do it? And of course, there's a constraint that we have to have supply that's equal to demand in each time period. Okay. So there's several options. We can produce energy from carbon-free sources. We can store energy from different time periods into the current time period. And not doing this. Okay. We can not use energy, which is equivalent to producing it through either efficiency or conservation. And I'll talk about the difference between those in a moment. So this is based on a model of a fully renewable electricity system for Mauritius, a small country in the South Indian Ocean. I was there with a Fulbright scholarship last year on sabbatical, so that's why the model happens to be about Mauritius. It's about the size of Rhode Island. It's about 30 miles by 40 miles and about 1.3 million people. So pretty small place. It's an isolated electric grid, so it's a relatively easy place to study, small scale place to study. And it has all of the conventional renewable energy sources, wind, solar, biomass from sugarcane, a little bit of hydropower, small island, so not a lot. In the context of this conference, the Energy A+B, this is definitely A. These are all technologies that are commercially available today. And the question is how to deploy them in a way that would provide all the energy, all the electricity at least, from renewable sources. So a basic principle of microeconomics is that at the minimum total cost, which is what we're looking for, the marginal costs of all the different sources should be equal. This example, sort of simplified example, shows hydropower as one possible source. Hydropower has been used a lot historically, mostly because it was the least expensive way to get renewable energy or to get any energy form. But the quantity is, of course, quite limited. The number of good hydropower sites is finite and small. And as we get into less good hydropower sites, the marginal cost of producing energy increases from those sites. Wind power is somewhat more available than hydropower. It's quite site dependent. You probably know that windy sites are much better, much less expensive to produce wind energy from than sites that aren't so windy. There are more of them than hydro, so it's a more elastic supply, but it's still somewhat limited. Where solar energy from photovoltaics or other kinds of solar sources is widely distributed around the world. In the past, it's been by far the most expensive one, the highest marginal cost to start, but the most elastic supply curve, meaning virtually any quantity of solar energy could be provided from photovoltaics. If you put those all together into an aggregate supply curve for renewable energy, it would look something like this. And the equimarginal principle says that the marginal cost of all those things should be equal for the quantity of energy that we use. And it's just a substitution principle. If there were additional hydropower that were available for a lower cost than the solar energy, then of course we could reduce costs by using more of the hydropower. And at the minimum total cost, no more of those substitutions are available. So then the other piece that doesn't get looked at quite as often is what about efficiency and conservation? Is that coming? Right. That also has a supply curve, a marginal cost curve. It's actually an upward sloping supply curve, but it slopes up from right to left. So it slopes upward as we reduce the amount of energy, the quantity of energy that's required. And the same marginal cost principle should apply. The marginal cost of efficiency should be the same as the marginal cost of production. Otherwise, it would be cheaper to implement more efficiency. So that's the basic theory in a static, simplified sense. The marginal cost of energy changes over space. It changes over the quantity that's required. I'm using marginal cost now in a slightly different sense than other speakers have. It's not the same as a market context. You might think of it as the perspective of an energy planner. If you were an energy planner and you were trying to get energy for your country or your region, what are the various sources and how much does it cost you to get another unit of energy from a particular source? So you could think of LCOE, levelized cost of energy, subscript I, as the cost of another unit of energy from another point in space in your country. And the solar availability, the wind availability, all those things change over space, so the marginal cost changes as we go to different areas. So that's one dimension. Here's how I would calculate this. This is the same as the formula for the levelized cost of energy. We're just looking at it from the energy from a particular location. So the capital cost times a capital recovery factor, alpha, plus the operating cost, which is often close to zero for renewable energy sources, divided by the amount of energy that's produced at the location. With renewable energy, we have this variability problem, which is to say that there's a temporal dimension and that the marginal costs change over time. Today in Cambridge on the MIT Common here, it's a bit cloudy. We could get solar energy today. If you were the energy planner and you needed to get more energy today for MIT, you could put solar panels out there and get electricity, but it would take more panels than it took yesterday when it was much sunnier. So the marginal cost of obtaining solar energy today, here, is much more than it would have been yesterday at this time. So this marginal cost of energy changes over time. And there's another formula that we could use to calculate that, very similar, except the denominator is how much energy would we get under conditions that are similar to today, under particular conditions, which could have to do with wind or sun or whatever are relevant to the source. And for the Mauritius model, as we map these out, if we calculate the levelized cost of energy subscript T for each time period in the year, you can see solar in orange and wind in blue. They vary tremendously from very low costs with a seasonal trend to costs that approach infinity for wind on what are windless days, of course. When there isn't very much wind, it's virtually impossible to produce energy at a reasonable price from wind turbines. So what starts out as a relatively simple, smooth, differentiable supply curve ends up actually being a supply surface in 3 dimensions with price on the vertical axis, time on the first horizontal axis, and quantity on the second horizontal axis. So we have these marginal costs for which the equimarginal principle should, in theory, apply, but the marginal cost profile is very complicated. And it's complicated by the fact that we'll probably add energy storage to this system as well. So we could take, for an additional cost, take energy from a previous time period and move it to the current time period. So quite complicated. In a theoretical model, we can identify the minimum cost of energy using the Lagrangian approach. You may have seen this, where the objective is to minimize the total cost subject to some constraints. The constraints here, very simplified model, solar, wind only on days 1 and 2 only. The constraints are that the supply be greater than or equal to the demand on each day. And I won't run you through the whole thing because it would be boring and it would take too long. But the important points are that since we have inequality constraints here, it's not feasible to make the solar and wind production exactly equal to demand in every time period. There's going to be some extra on the days when it's really sunny. Because we have the inequality constraints, the Kuhn-Tucker conditions apply, which deal with the border conditions, boundary conditions. And when you run through all those conditions, what you find is that in particular circumstances where the demand constraint is binding, so where the supply of wind and solar exactly equal the demand, in those times we have equal marginal costs. So the equimarginal principle, basic principle of economics, does apply, but it only applies at these certain critical design times. Times when there isn't very much wind, when there isn't very much sun, times when it's difficult to provide energy. So we're basically trying to move beyond this paradigm of average cost, levelized cost over time, and look at the specific times that will drive the design of a renewable energy system. And that's difficult because of the complicated nature of the marginal costs for the variable sources. So empirically, what we use is a software. This is a linear programming model called Osmosis, where we map out the energy demand as well as the potential energy supply from various sources, in this case over the course of 1 year. We put in for Mauritius all the potential sources and what their capacity factors would be on each day of the model year, so reflecting how sunny it is, how windy it is, the seasonal nature of the hydropower production, all that sort of stuff. We put in the capital costs and the operating costs for each of those energy sources, as well as capital and operating costs for energy storage, and the model figures out what's the least expensive portfolio of sources that meet supply where supply meets demand at in every time period. In this case, we had 730 time slices each day and each night of the model year. And there's always some extra. You know, a lot of the things I read on renewable energy seem to start with the assumption that we will utilize all of the energy that's produced. But from an economic point of view, it's just not realistic. We're essentially designing for the difficult times. And in the good times, when it's very sunny and it's very windy, there's extra, and that's the least expensive way to design the system to provide renewable energy at all times. So don't start with the assumption that we have to use all of it. There's always 10 to 20% that ends up being left over and presumably would go to some useful purpose. So here are the results for Mauritius. Roughly thirds of biomass, solar energy, and wind energy, and a little bit of hydropower and some other things. For all of these models that I've run, and Ming, my associate, has run some other models on a different island in the same area, we always end up with these mixed bundles. The idea that some of the sources are complementary over time seems to be prevalent. And all the other simulation studies that I've seen come to those conclusions as well, that we're virtually always going to end up with a mixture of renewable energy sources. Okay, so that's the setup, that's the context. Here's the question: what's the value of efficiency and conservation in that context? And these two things are slightly different. Efficiency means using technology to reduce the energy demand for the same energy service, a more efficient light bulb, a more efficient motor, something like that. Where conservation means changing behavior in some way to reduce the use of energy. So that implies giving up or changing, at least, the energy service that you're receiving. And for this context, for Mauritius, as well as I think in most places, if we were to implement efficiency measures, essentially those shift the demand curve down. If it was something that ran all the time, it would literally shift it down the same in every time period. Not everything runs all the time, but nonetheless, we get a pretty predictable shift of the whole curve, where conservation could be much spottier. It could be at only specific points in time, and to the point of this presentation, it could be targeted at the points in time where the energy is the least available, and it would therefore have the most value. And so this is what we end up with. The dotted line on the bottom is the levelized cost of energy for the whole system, which was about 12 cents per kilowatt hour in the case of this model for Mauritius. The blue line is the effective efficiency, which is 25% or so more valuable than the average cost of energy. Essentially, the efficiency is replacing the last most expensive energy source on average over the course of the year. So we should be spending more on efficiency than we do on average for production. But the conservation returns were much, much higher. What we did here was selected the 12 time periods in the year that were the most constrained in terms of solar and wind energy. And essentially that meant nights, when there's no solar energy, that didn't have any wind, or virtually no wind. So windless nights in this energy model are the times that are most expensive to supply. And if we reduce the energy from 2% up to 20% during those times, we ended up with a pretty flat curve, but we end up with very high energy savings, about 7 times the value of the average cost of producing energy. So there's certainly an incentive to reduce energy use at these periods of time. How to get consumers to respond to those incentives is a question of what kinds of programs would be set up. The previous presentation had a nice study of China and some of the ways that consumers can be prompted to use less energy. That was not looking at specific points in time, but it could be adapted to that kind of a strategy. So our conclusions were that efficiency has a somewhat greater value than production on average. Therefore, we should be focusing more on efficiency. If you've studied this at all in the US, you know that now we focus much less on efficiency than on production. So that paradigm needs to change somewhat if we're to optimize cost, to minimize cost. That conservation at these critical times has very, very high value, and so there's an incentive to focus more on that. But these critical times are not predictable in advance. They're not even very easy to identify after the fact, but there are these specific times when the utility could, in principle, let consumers know that this would be a time to conserve energy and could provide a payment or some incentive for people to cut back at that in those particular times, or perhaps to industrial users who have more flexibility to change their demand as needed. And there's lots of new technologies that could help to make that viable, as the last presentation suggested as well. A question for future research is how much energy could be saved in this way. In our study with those 12 time periods, the value was very high, but the quantity was pretty low. It was only about 0.5% of the total energy that was used over the course of the model year. And if we wanted 1% or 5% or 10%, what would the value of that be? And what would we have to pay consumers or industrial users in order to make those gains? So that's where we are. Questions?
Thank you very much. So, any questions? Yes, please.
I really like the concept of conservation being a huge game changer for decreasing the cost. Maybe, I don't know if it's eliminating gas peaker plants, but you assume that that's what they're there for. Can you comment on that? And you said to get consumers, why not have these utilities? Are they, is it because they're passing the buck on to consumers today? Why are they not, or why do you not say it's utilities who should be pushing this conservation?
Sure. Well, I guess my assumption is that an end user of some sort has to reduce their use of energy. So it could be a consumer, a residential consumer, it could be commercial, educational, it could be industrial, So someone who's using energy has to stop using energy at this moment.
Fixed price for
Indeed, they have to have an incentive to do this, right? So there has to be a market mechanism or some other mechanism to let people know that this is one of those times and then compensate them for doing it. And I guess the basic economic principle is that if there's a payoff, if there's this 80 cent per kilowatt hour payoff, then some contractual arrangement will be made so that this can be implemented. In Mauritius, so for this particular model, there's no fossil fuel. This is all renewable energy. There's the equivalent of the gas peaker plant, which is ethanol engines. Mauritius produces a lot of sugarcane, so one possibility was to convert some of the sugar to ethanol and use those engines for the very difficult times. Quite expensive as a strategy, so not used very many hours in the year, and that's what would be replaced during those very expensive times. But it might also be reducing the size of the battery storage or something like that. One of those relatively expensive strategies that we would rather not use, but we have to. The economics of this really boil down to how little energy storage can we get away with. The energy storage is expensive and it doesn't produce energy. It just moves energy from one time to another. So basically the strategy is to array things so that as little energy storage as possible is needed, and if we can replace that, there's a large payoff for doing it. Any question?
Any more questions? Thank you very much.
Yeah, thank you.